energy of a dipole in a uniform electric field. Let's see this. This is the uniform electric field pointing in the rightward direction, shown by these arrows. We have a dipole. The length is not given, but the length is 2L. This dipole moment makes angles theta with the field. Now here it is having some energy. Whenever we do whenever work is done by external agent, the energy of the system increases by the amount of work. Now suppose here we are turning this dipole by the small angle d theta from its initial position. This was its initial position. Here it was turned by a certain small angle d theta. While making it turn this way, some external agent has to do work, and that work done gets stored in the system as its energy. So we can say here increase in energy du is equal to work done by external agent. Basic formula for work is force into displacement, but here there is rotation. So instead of force into displacement, we'll use torque into angular displacement. So there's torque into the angular displacement. This external torque is almost equal to the torque due to the field, that is Pe sin theta. So this torque external is Pe sin theta. D theta is missing over here. It should be P sin theta d theta. And here further, here even this d theta is missing. So net energy is integral du is integral P sin theta d theta, the missing part d theta. We'll integrate this to get this total one. Again here in this same expression we are having this d theta missing. We'll put the limits. When theta is 90 degree, this we are arbitrarily assuming that when theta is 90 degree, energy is 0. Means when this dipole is oriented this way, perpendicular to the field, we would consider its energy to be 0. And at any other angle theta, the energy is u. So this, on simplifying, gives us this expression. U is minus Pe cos theta. This can be very easily simplified, and finally you have this expression. So energy is minus Pe cos theta, minus Pe cos theta. This is the basic formula for energy. So this expression clearly tells you that as the value of theta increases, the energy increases, and as theta decreases, energy also decreases. When theta is 0, energy is minimum. The basic formula. Now let's see this. This is the example of uniform electric field again, where the dipole is oriented parallel to the field. Dipole moment from minus q to plus q, rightward. Field is rightward, dipole moment rightward. Theta 0. Energy should be minimum. So energy is minus Pe. E is parallel to P. Theta is 0. Energy is minimum, that is minus P. Let's see the other case. If we orient it perpendicular this way, this time E and P are perpendicular. Theta 90. Energy is 0. Now if the dipole is having its dipole moment opposite to the field, as over here, dipole moment from minus q to plus q this way, field directed rightward, they are opposite to each other. Here energy is maximum. This is the expression for energy. So this is the examples or the special cases for energy of dipole in uniform electric field. Now let's see what is its use. whenever we are making a dipole turn through a certain angle, work has to be done against the electrostatic force, and we'll derive the formula for that work done. We'll not derive it, rather we'll express it in terms of energy. Now here, this is the initial configuration where the dipole moment vector, this one dipole moment vector, makes angle θ1. So here energy is initially minus PE cos θ1. Now suppose this is rotated this way, so that the dipole finally forms angle θ2 with the field this way. It's rotated so that this angle between the electric field and the dipole moment becomes θ2. This one becomes θ2. So the final energy is this much. And work done by external agent can always be written as final energy minus initial, UF minus UI. Put the values, we get this one. So this is the formula for, basic formula for work done in rotating a dipole in a uniform electric